theorem. It is sometimes called the fundamental theorem of arithmetic. It says that if I have a natural number, say at least 2, then there exists prime numbers and this list of prime numbers I have written need not all be distinct. Some of them could be the same, as we saw in the earlier example. We had many 2s and 4s and so on, sorry. We had many 2s, I guess 3 and 5 only occurred once, but 2s repeated many times. So, P1, P2, Pk, there exist prime numbers such that n can be written as a product of these primes. So, this is the first statement, and there is a second part to this. So, this is the existence of prime factorization, and there is a uniqueness statement. So, this is similar to, for example, the division algorithm and so on, where we said if you have a number a, you can find a quotient and a remainder when you divide it by a number b, but the quotient and remainder are in fact unique. Okay, so there is a similar statement here. So let me just say it is these primes which occur, there is uniqueness up to reordering. This is sort of how one states this. Okay, but one has to write this out formally a bit carefully. So the uniqueness statement says the following: suppose I have another list of primes, if q1, q2, ql are also primes, such that n is the product q1, q2, ql, then what we would like to say is that firstly the number of terms that occur in the first and the second expressions are the same, k is equal to l, and we would have liked to say that, and the primes are, they match, p1 is the same as q1, p2 is the same as q2 and so on, but that may not actually happen in practice. So, for example, the thing we did for 960, or let us take a smaller example, if I had 2 into 2 into 3, that is 12. I could rewrite this, I could find another expression as 3 into 2 into 2. So, all I have done here is just the same factors essentially, but I have sort of permuted the order in which they occur. Okay, so of course that's something I can always do, and what this uniqueness says is that that's the only thing you can do, that's the only thing that can be different. If you write another list of prime numbers, then they coincide with the first list after you have reordered the factors. So, let us complete this sentence and we can rearrange q1 to ql in some order. Okay, so let us write them down, say I will just call that rearranged as, so the first term could be maybe q3, okay, so the I1 is 3, qi2, qi3, qil. So, this is often how one denotes this in some order, qi1, qi2, qi3 till qil, where what are the i's, I1, I2, IL is some permutation of the numbers 1 to L, is a permutation. Of the numbers 1 through L, such that after you have reordered, the prime P1 coincides with Qi1, P2 coincides with Qi2 and so on. Pk or L, they are the same, Pl coincides with Qil. Okay, so this is the uniqueness statement, and observe that, I mean it was sort of an easy thing to sort of understand and state in an example, but when one wants to write it out formally as a mathematical statement, it becomes somewhat cumbersome, okay, and this is sort of unavoidable in many situations. Anyway, so let's prove these statements. So the very first statement says that there is existence, and we have intuitively seen how to do this. You sort of keep breaking a number down, but to sort of prove it economically, it might be easier to say use induction, for example. Okay, proof. Let's do this proof by induction. Okay, so we need to show that every number at least 2 can be written in this way. So the very first step of the induction, what is the smallest value of n for which we have to check this? Take n equals 2. Okay, n equals 1, it really does not make sense. So for n equals 2, observe 2 itself is prime. So there is nothing further to do. So n has been written just as the prime 2. So 2 is a prime. So this is the required expression. So done. You just have to write it as a product of primes. In this case, there is only one prime number which comes in the product. Okay. Now let us assume the induction hypothesis. So assume the result to be true, that is that n has a prime factorization for all natural numbers which are smaller than n. Okay, all natural numbers which are at least 2 and smaller than n. So maybe I should say, so now I picked, let n be some natural number. Assume the result to be true for all natural numbers k between 2 and n, strictly smaller than n. Okay, and now we have to show, so this is strong induction if you wish. Okay, this is sometimes the principle of strong induction, which means you assume the result for all natural numbers smaller than n, then you prove it for n. Okay, now we want to prove it for n. Okay, so let us see what we want to prove, that n has a prime factorization. So we have n. So all we do is just that tree, that process that we did in that example, we just start with that. Okay. So observe there are only two cases, either n is already prime, case 1 n is prime. In this case we are done, there is nothing to do. The expression is just like in this case, n itself is a prime, you have written it as a product of a single prime number. Okay. Or case 2, n is not prime, in other words n is composite. Now what does it mean to say n is composite? This means that n has a factor which is not 1 or itself, right, it has a strictly smaller factor. So n can be written as a product of a and b, where a and b are strictly smaller factors. So a and b are not 1, they are not n, they are strictly between 1 and n. Okay, so now we will do the following, we will apply the principle of induction. So by the induction hypothesis, both a and b have a prime factorization, because both a and b are numbers strictly between 1 and n. Okay, and that is what we assume for numbers between k, here I wrote greater than or equal to 2, that is the same as saying strictly greater than 1. So by the induction hypothesis, both a and b have a prime factorization. So what does this mean? This means that a can be written as a product of prime numbers and b can be written as a product of prime numbers. So you write a as p1, p2, pk, b as another set of primes, p1 prime, p2 prime, maybe we will call this something else, p d and p2 prime, p prime e maybe, and all you have to do to get a prime factorization for AB is just put them together. So the total product AB is therefore just P1, P2, PD followed by P1 prime, P2 prime, PE prime. Okay, so that is the existence. All you had to do was to demonstrate or find a list of prime numbers so that the number n is a product of those primes. So, in this case we have written n like this. So, that is the existence statement. Let us do the uniqueness as well. So, the uniqueness says if you could write it in another way. So, if I have P1, P2, PL is the same as, sorry, this was K, it is the same as Q1, Q2, QL, then the same primes occur on both sides, sort of up to a reordering. Okay. So, let us do this. So, this is what is given. Now, observe that, so let us start with the first prime number P. So, let us take or consider P to be P1, the very first prime number. Now, what all do we know about it? This is a prime number. It divides the left hand side because one of the terms on the left hand side is this number P, and therefore, it divides the right hand side as well. So, P therefore divides the right hand side. Okay. Now, remember this lemma that we proved about prime numbers, which said that if a prime number divides a product, it must divide one of the terms. Okay. So, recall our lemma. It said P divides AB, then P divides A or P divides B. Okay. Now, we are sort of in that situation here. So, this prime number P, it divides, well, it does not divide a product of two things, but rather a product of L different things, but we can think of it as a product of two things like this. So, look at the following statement. I will think of the right hand side as Q1 times Q2, Q3, QL. So, this is like a product of A with P. So, what does this mean? This means that either P divides A or P divides B. So, I conclude either P divides Q1 or P divides the product of the remaining terms. Okay. Now, in this case, fine, I do not do anything. If this happens, I just repeat my argument. So, if P divides a product of Q2, Q3, QL, I apply my lemma again in this case. Okay. So, then I conclude that what does this mean? This tells me that either P divides the very first term or it divides the product of the remaining terms Q3 onwards, etc. Okay. So, if I sort of keep going L times, here is what I conclude, that either P divides Q1 or if that does not happen, it divides Q2 or it divides Q3, etc. So, I conclude that this prime P must divide one of these primes on the right hand side. It divides Q1 or it divides Q2, Q3 and so on. Okay. But observe that this is a very sort of strange situation. I have a prime P which is dividing another prime Q1, right. So, when can this possibly happen? So, suppose can one prime divide another prime is the question. So, if P is a prime and if Q is a prime, and if this prime number P divides the prime number Q, well, what does it say? It just says that those two numbers are the same. Okay. So, when can a prime number divide another prime number? If P divides Q, the claim is P must equal Q. Okay. Why is that? Because we can see what the divisors of Q are. The only divisors of Q, the only positive divisors, let us say, I will ignore the negatives for now, the only ones are 1 and Q itself. Okay. And now I am saying that this prime number P is one of the divisors, P divides Q, right. What does that leave me with? That only leaves me one option. P can't be 1 because P is a prime number, it is bigger than 1. The only thing it can be is the other divisor, which is Q itself. So, it says that P equals Q. Okay. So, in this case we conclude if the prime number P divides the prime number Q1, this is just saying P must be Q1, or if this happens, it means P must equal Q2 or and so on. So, we conclude that this prime number p must equal one of the primes which occur on the right hand side, okay, and that is sort of the thing that we want. So, this was what was given, and we concentrated only on the first prime which occurs here and found that that prime occurs also on the right hand side. So, what we do when we see the same term on both sides, we are usually very happy, we cancel that term from both sides, okay. So, I take P1, so maybe I should just rewrite this whole thing again. So, I will say I have P1, P2, Pk, then I have Q1, Q2, Ql on the other side, and I know that this P1 is the same as one of the Qs, let us say it is Qj, okay. So, what we like to do is to cancel the same term which occurs on both sides of the equation. So, I get rid of that term and then I am back to where I began, right. Now, it is the same problem except I have got P2, P3, Pk, there is one fewer prime number on the left hand side and one fewer on the right hand side. So, Qj is gone, Ql. So, this term Qj that was there is no longer there, okay. But now I can repeat the same argument. I can say, well, let us start with this prime number P2, apply the same argument and conclude it must occur on the right hand side, it must be one of the terms on the right hand side. So, I find whichever term that is, I cancel, okay, and I keep going like this, okay. So, continue the same process. Now, what will happen? Well, one of two things. So, firstly, let us show that k and l must be the same, okay. First observe that because I can keep doing this process, my first claim is that this tells me that k and l must be the same, okay. Prove what are the other possibilities, otherwise k is either strictly smaller than l or l is strictly smaller than k. These are the only three possibilities I have, okay. So, let us look at one of them. Suppose k were strictly smaller than l, then what would have happened? I would have kept doing this process at every step, finding one thing on the left which would cancel off something on the right, okay, and I would have cancelled all of these. I would have cancelled k terms from the left, but there would still be some terms left over on the right hand side, right. So, LHS, the left hand side, everything is cancelled and it became a 1. The right hand side would still have a product of L minus k terms, L minus k prime numbers. So, of course, this is not possible, right. A product of L minus k prime numbers, so L is strictly bigger than k means I have at least one prime number, such a product can't equal 1. So, therefore, this can't happen. Likewise, if the other thing happens, this cancellation would have exhausted all the terms on the right hand side, I would still be left with some things on the left. So, neither of those can happen. So, the number of terms has to be evenly balanced on both sides, same number of terms on both sides. And in that case, what we have just shown is that every prime which occurred on the left can be matched up with something which occurred on the right, right. I was always able to find one term on the other side with which I was able to cancel it, okay. So, this is the end of the proof. So, that proof is done. Okay. So, this is an important statement. So, this existence and uniqueness is called the fundamental theorem of arithmetic.